Hello, I'm David. I'm the coordinator of the Maths Learning Centre at Uni of Adelaide, and this is a revision seminar for Data Analytics. It's Semester 1, 2023, and we're going to just talk about a whole lot of random things as we go. Okay. Well, I'm going to start with probability things. And in particular, I've been asked about notation. Bear with me a sec. Okay. So, okay. So just a probability is a comparison between what has happened or what you think you would like to happen, or whatever it is you're thinking about, and all the things that could have happened. That's what probability is. And one of the reasons that they want to they want you to do things with probabilities is because they're leading up to hypothesis testing later on, which mention probabilities along the way. And so most people who teach statistics believe strongly that if they do a whole lot of things with general probability notation, that the hypothesis testing will make more sense. I'm not 100% convinced that it works, but here we are. So probability is still an important thing to think about, and so we're going to think about it. So as I said, comparison between the things you're thinking of and all the things that could or could have happened. And that's a really important way of thinking about it. You can't know what the probability of anything is unless you know all the things that could happen and how likely they all are. So that's really important. All right, so that's just the beginning. So the next stage with the probability notation is that we tend to write the probability of, and then we put like a sentence here. So the probability, or the probability that, or the probability of. So the probability that the dice roll is at least 7, or the probability of a person being both over 50 and studying at Uni of Adelaide, and various other statements like that. And so what happens is that this probability of or probability that becomes a P, and then you can put the sentence in here. And that's how they often use it. Do they just use P in this course, not PR? Okay, good. So already a point of difference for some other courses. And if you're really lucky, then you'll be able to write that sentence in terms of maths notation. Okay? So if you're really lucky, you might be able to say x is greater than 7 or something like that. So that is one option for how we think about probabilities. The other option for how we think about probabilities is that the thing we put inside here is the name of a set. I know that your lecturer probably hasn't talked about it this way, but this is the other way of doing it. The name of a set of options, actually they would call them outcomes probably in this course. So just reminding you now, I'm making this up as I go along because I didn't know what I was going to talk about before I came. So sometimes I'll backtrack and change what I say. So, cool. So instead of having a sentence in this spot, you may just have a letter like A or something like that. So e.g. A or A intersection B or something like that, that sort of thing. So we get to decide which way we do it. We can't mix them. Some people do, but that's not how we do it. And so it's very common to say something along the lines of, let A be the event that a person is over 50, that sort of thing. And so that letter A is standing in for an entire sentence, but it's really standing in for the collection of people for which that sentence is true, or the collection of moments in time for which that sentence is true. And so I guess that's the idea. So when you say, so you might say, let A be the event that a random person is over 50, and then you would say something like the probability of A, something like that. That's just an example of how it would go. Cool. Just setting up. And so you can flip between them. Yeah. So the reason I'm talking about it this way is that we tend to draw a picture of all of the things that could happen as a sample space, which is a rectangle, and then draw circles inside it to represent the different collections of objects that we're interested in. I wish I had a deck of cards. I'm trying to decide if I'm going to go and get one. I will. One moment. All right, here's my deck of cards from the Adelaide show. Cadbury. So I'm just going to use these 12 cards. So I could talk about the probability that the person pictured has a moustache, for example. And that's this person, that one, not this one, none of these people, and none of these people. So the probability that the card has a person with a moustache is 1, 2, 3, 4, 5 out of 12. And so that's that. I will actually write some things down in a minute. And the probability that your person is holding a sword. I'm going to do a sword. Nah, let's do probably that your person is looking to the left, which is well, the top face is looking to the left, which is this person, this person, this person, this person, this person, this person, this person. And so that's 1, 2, 3, 4, 5, 6, 7, 8 out of the 12 people. Okay, that's great. But then I could say, what's probably of both having a moustache and looking to the left? Well, that is these people and this person. That's only 3 out of 12. And so you can combine the groups together. And that's just what I wanted to say, that I wanted some things that weren't classic probabilities. Wanted something that was a bit more fun than that, that aren't necessarily independent of each other. So, cool. I'll come back to that example in a bit. But I have, so I could say, just as an example, the 12. The 12 picture cards in a standard English deck. And I could say that so I could talk about it this way. I could say, and choose one at random. So I could say the probability that the person has a moustache, right? And I could write it with a sentence in that spot, like, well, no, that is a sentence. The person has a moustache isn't act a sentence, it does have a verb in it, so it's a real sentence. I could do it that way, and that came out to, what was it, 5 out of 12, was it? Can't remember now. And I could do that, but I could also say that M be the event the person has a moustache, and write the probability that M is 5/12. That's totally a way of doing it. Officially, if you want to use letters, you're supposed to say what the letter stands for, like that. So there are two options for the way that you could write it, like that. Officially, this takes longer to say, but it's something that we can now borrow our notation in a minute, and we could say let is looking left, and so the probability of L is 8 on 12, we could say. And so now if I wanted, so here's the thing, if I wanted to talk about the event that the person has a moustache and is looking to the left, that is the event M intersection L. It's both things simultaneously. So this M is standing in for the collection of all the cards that have a moustache, and this L is standing in for the collection of all of the ones that are looking left, and the intersection is the collection of that is all of the ones that are in both of those collections simultaneously. That's what this means. It kind of means and in that context. So if you read the sentences aloud, if M stands for has a moustache and L stands for is looking left, then this means has a moustache and is looking left. So when you read it aloud, when you read the rule aloud, it'll be and. Whatever M stands for, and the word and whatever L stands for. But when we say and, we mean that both of the rules for being in that thing are true at the same time. Like the rules are and, as opposed to it's not gluing the two things together, it's finding the ones where you're in both of them at the same time. So it's the rule has an and when you say it aloud. Yep. Let's talk about that too. Yep. let's do it. I actually do want to do that too. So I'll do the calculating in a second. Remind me if I don't get to it. But I will do the union first. So just drawing a picture. Hello. Oh, we can hear you. So I'm just going to draw a picture of it. And so I had the King of Diamonds and the Queen of Diamonds and the Jack of Diamonds and the King of Clubs and the Queen of Clubs and the Jack of Clubs and the King of Hearts and the Queen of Hearts and the Jack of Hearts and the King of Spades and the Queen of Spades and the Jack of Spades. And so when I did M, the ones with moustaches were the King of Diamonds, the Jack of Hearts, the Jack of Spades, the King of Spades, the King of Clubs, and there's our 5 with moustaches there. So that's our M. And then the ones with looking left were the Jack of Diamonds, the King of Clubs, the King of Hearts, the King of Spades, the Queen of Hearts, the Queen of Spades is not, Jack of Spades, Queen of Clubs, Queen of Diamonds, Jack of Hearts, and the King of Diamonds. So they're all the ones that are looking left. And so the ones that are both, that's the intersection. So M intersection L is the ones that are both. That's the idea. So both of them simultaneously. And when you draw it in a Venn diagram, you do the overlap between them. But this is a little this is a bit more spread out, like that. And the union is all the ones that are coloured in at all. So M union L is all of this. It's the combination of the two of them, and it is, and you normally read that union sign aloud as OR. So M union L as moustache or left looking, right? And so this is OR. But when you say the OR, it's about the rule for being in that collection. The rule for deciding if you're going to count that in your probability is that it's one or the other, or both. It doesn't matter. It's not exclusively or, it's just one or the other or both. And so I've got that the probability of M was 5/12, and the probability of L was 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9. I must have missed one before. I really thought I had them all. Anyway, it is 9/12 now, and the probability of M intersection L is 4 of them, and the probability of M union L is 9. Is 11 of, is 10 of them. Is that right? Yeah. Something like that, according to this picture so far. Because there's only 2 that are missing and there's 12 total. All right. So you can't just calculate them by multiplying the probabilities. And that's because if you are looking, if you have a moustache, you're really likely to be looking left. But if you don't have a moustache, possibly slightly different probability. So I think that that's about conditional probabilities, that knowing one of them changes the probability of the other. So I can tell that these things aren't independent. Now let's just do one more calculation. So the probability of, that's this thing here, and this is pronounced usually given. But in my head it's out of. What's the probability of having a moustache, but only out of those that are looking left? That's what that says. And so for me, the number that are looking left is 1, 2, 3, 4, 5, 6, 7, 8, 9. So it'll be out of 9 because we're only looking at the ones that are looking left. Yep. This is called conditional probability. It's only out of the ones looking left, and so it's only out of 9 because that's how many ones are looking left. And the 1, 2, there's 4 of them. Out of the ones that are looking left, 4 of them have moustaches. Because I'm ignoring all the ones that aren't looking left, and so these ones here don't count.
So basically, whatever's on the right of the equation is going to be the denominator?
Yep, whatever's after the given sign is in the denominator. Is that what you meant?
Yeah.
Yep, that is correct.
Okay. Thank you, cheers.
But the other way around, the probability of L given M, there's only 1, 2, 3, 4, 5 that have moustaches, and out of those, it's still 4 that have within that. So within the moustaches, there's 4 that have looking left, and so it's 4 out of 5. Yeah. So things are independent if the conditional probability is the same as the original probability. So probability of L just all on its own was 9 out of 12, which is the same as 3/4. And 3/4 is not the same thing as 4/5. This is 75%, and this is 80%. So since these are not the same, they're not independent. So the probability of just L on its own is not the same as L given M. So L and M are not independent. But if they just so happen to be the same probability, then they would be independent. So this is saying that, like, we've got if you pick out of all the possible cards, you've got a 75% chance of getting a left-looking one. But if you pick out of just the moustaches, it's slightly higher percentage. It's a little bit more likely to pick a left-looking one if you're only picking out of the moustaches. And so knowing that you've got moustaches already changes how likely looking left is. Yeah. And it doesn't have to be that different, it just has to be not the same. It could have been 0.75 and 0.76 and it would still be not independent. Yep. Cool. People got on fire with the good questions today. I'm very excited. So, if you know in advance that things are independent, that's the situation in which you can multiply. But adding is when you are... actually, before I get to that, I just want to do one thing. Okay, so just one more example. In this example here, the probability of M union L was 10 out of 12. Oh, actually, I've got all these things written down. Just a second. I'll write them down again. All these 4 probabilities are all related to each other. The more that M and L overlap, the smaller their union intersection is going to be relative to each of them. So I'm going to draw a new picture of it. These are the M's and these are the L's. I've drawn it upwards instead of sideways, I'm sorry, but it fits into my page there. This bit where they overlap, that's M intersection L. And the bit, this entire thing that includes all of them together, that whole double circle thing, that's M union L. That thing, all of it. So it turns out that if I want to figure out M union L, if I knew what M was, and I took off this bit where M intersects with L, and I added on the bit with L, that would produce the entire of this thing here. And so I end up with this formula here. Like that. Is that a formula that looks familiar? Yeah. No, this has got nothing to do with being independent. This is always true all the time. It's just that if they're not independent, you just have to draw this whole diagram to figure out what this bit is anyway, and so it's a bit of a moot point. But just to check that we've got it, let's just look at this. The probability of M was 5/12, and the probability of L was 9/12, and together that was 14/12, and we took off the 4/12, and so that's 14 minus 4/12, which is 10/12, which is the correct answer. It all works neatly. And it works the other way too. We can switch these two and it's fine. And the reason that works is it's literally drawing the picture, is that to get this bit, I can add this bit and take off that bit, and then that leaves a nice little hole to put the L in, basically. Yeah. And some people talk about if we added these two bits together, then we would have counted that bit in the middle twice, so we have to take it off so that it's not double counted. Yeah.
One question, sorry. So what is that formula? Why did you do that formula?
This formula is if someone didn't tell you all of the information about this thing. Now, we were able to get it all directly from our drawing of the actual cards themselves. But if someone only told you this information and you wanted to know what M union L was, you could figure it out from that.
Oh, okay, perfect. Thank you. Cheers. Thanks.
Yeah. So that's why you have it. And your lecturers, as far as I can tell, and all the kinds of questions that they ask you in the tutes and stuff, are that kind of people. It's like, oh, cool, I'm just going to give you some of this information and you have to figure out the other information. That's like very mathsy thing to do. Very physicsy thing to do as well. Like whenever there's formulas, people love doing that. They say, oh, we've got a formula of 4 things. I'll tell you 3 of them and you have to figure out the other one. And that's what they're, that kind of thing that they do. Okay, so just so you know, this is one of the situations where we have to add things to figure out a new thing. We also have to subtract as well. If you're very, very lucky, they won't overlap at all, and so this bit will be 0. And then you'll just add them. So they call that being mutually exclusive. So I don't know if I can think of mutually exclusive things in this particular set of cards. Oh, having a moustache and being a queen in this card are mutually exclusive. Not impossible in real life, but in these cards, possible. I'm going to talk about that. That is a great question. But I'm just going to point out something, that if the probability of A and B is 0, that is A and B can't happen together. It can't happen at the same time. That's called being mutually exclusive. So e.g. in our cards, if M is having a moustache and Q is being a queen. This is a bad writing, I'm sorry. It should actually be a full sentence here. Like, having a moustache and being a queen, I should just point that out, then the probability of M intersection Q is 0 because none of the queens have moustaches. Let me just check. No, 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 no. Most of them have sour expressions, but they do not have moustaches. So we're all good with that. And so when you draw the picture of them in the deck, and you have all your moustaches, which were here, they're my moustaches, and they're my queens. They don't overlap at all. There's no options that are in both of them at the same time. And so that would be looking more like this in your Venn diagram. And so if you can reason out that they can't happen at the same time, then that is what causes them to be mutually exclusive. And you're asking, how is that different from independent? Okay. Mutually exclusive means it is impossible for them to happen at the same time. Okay? So I'm just going to write an extra piece of information down here. The probability of having a moustache was 5 out of 12, right? The probability of having a moustache, given that you're a queen, is 0. It's impossible to have a moustache if you're a queen. And these are not the same. And therefore, M and queen are not independent. Because that's what independent means. Independent means that knowing about queens would give you no information whatsoever about whether they have a moustache or not. But it does, right? Knowing they're a queen, definitely know for absolutely certain that they do not have a moustache. It changes the probability. They are definitely dependent. And in fact, this is the extreme of dependence. If you know what Q is, then you know for absolute certain whether you have an M or not. That is the most kind of dependent that you can have. The only other kind of dependent would be the other way around. It's like if you know something happens, then you know 100% that the thing does happen. And so this is mutually exclusive is the height of dependence. The word independent makes it sound like they're not related, but they're not related in a very special language way, not in a picture way. Yep. What's that? Independent means they're not related language-wise. One of them, you can't say one of them and know what the other one is. Yeah. Yep. Correct. I'm going to repeat that. Mutually exclusive means that they're not independent because the fact they can't occur together is a dependence. They do depend on each other because they can't happen together. So the other worst one is that something that can only happen when something else happens. So you can only be holding a flower if you're a queen, I think. Yeah. So not all the queens are holding flowers, but you can only hold one if you're a queen. And so they're dependent because one of them only happens when the other one happens, which is the complete opposite of mutually exclusive. They're mutually contained. I don't know what the word is. There isn't a word for it. Okay. So I just want to say one more thing about independence. Things are independent when the amount that the thing is out of everything is the same as the amount that it is out of just the other, out of the other. Blah, blah, blah. That doesn't make any sense. Here's a 100 by 100 grid. And I'm going to colour in 2 sets. So that bit there, that's 40% of the whole grid. 1, 2, 3, 4, 1, 2. Yeah, that's 40% of the whole grid. The probability of being blue is 40%, like 0.4. Bear with me. My pink text is running out, and of course it is. Very sad. Nope, it's going to have to be brown. So that bit there is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 35%. Okay, cool. So the blue is 40% of the entire thing. It's also 40% of the brown bit too. It's 2/5, which is 40% as well. This is independent. The probability of blue is 40%. And the probability of blue given brown is also 40%. They overlap in just the right way in order to be independent. That's what independent means for a Venn diagram. They have to overlap just right. If this was just over one bit, then the blue wouldn't be 40% of the brown. It'd be less than 40% of the brown. It'd only be 20% of the brown, and they wouldn't be independent anymore. And if they didn't overlap at all, it would also not be independent. So this thing being in different positions will change whether they're independent or not, and it can only be independent if there's exactly this bit here where they overlap in just the right way. So that's independence. They have to overlap just right, and then they're independent. Okay, so just the final moral is that things have to be able to happen together in order to be independent. And they have to also be able to not happen together in order to be independent. Yeah. And it's so hard for so many people to process this because the word independent sounds like they don't overlap. But it's not referring to the picture, it's referring to the information. Yeah. Oh. Yeah, mutually exclusive, this would be over here, they wouldn't touch at all. I mean, they might touch right along the edge, but they don't overlap. Yeah. Yeah. I like my 100 by 100 grid. It's very helpful. I will put it in the notes. It's in the Maths Learning Centre, and it also has probability rules on the back, words that independent means and stuff like that. So just for future reference if you ever want to borrow it. So the only other notation we haven't covered is the complement. So I think they use a bar in your course for this. And so this is the complement of A. That's the note thing, but I would read it aloud as not A. And so if M is having a moustache, this would be not having a moustache. And if the probability of M was 5/12, well, the probability of M bar would be 7/12 because that's all the other ones. That's how it works. And if the probability of that's pretty much it. And this is 1 minus 5/12. The idea is that if you add something, if you add M and M bar together, then you'll just add their probabilities and you'll get 100%. You'll get 12/12, which is everything. That's, yeah. What's that? Yeah, it's the opposite. It's everything that isn't part of this one. And so on a Venn diagram, it's like, well, these are the M's, that's M, and then everything else is M bar, all the rest of it. Yeah. And so the rule that they say is that the probability of A bar is 1 minus the probability of A. Because together they add up to 100%, and 100% as a decimal is the number 1. Yeah. Yeah. Oh. So I could totally, in my example, go the probability of M bar intersection L, and I could go back to my picture and go, no. Well, not M, which is all the ones that aren't pink, intersection L, which is this bit here, that's 5/12. So that's this bit here, because that's the ones that are not M, because it's M bar, which is all of these ones. And then L, well, these are the ones that are not M and also L. Probability of not moustache and looking left. So the bar you read aloud as a not, and the intersection you read aloud as an and so we get that. And then we can just literally count them. That's it. Which happens to be the same probability as M, but that's not really relevant here. There's only 12 possible probabilities I could get in this particular story. How are we feeling about the probability notation? A little better? Yeah. So it's really nice when you've got a diagram like the one I drew there that has everything neatly circled for you. But if you don't have that information, you're going to have to figure it out from scratch. So I'm going to do one more example. Suppose just a second. And all the clients of a vet, 80% have cats and 90% have dogs. And 5% have neither. If you choose a random client, what is the probability a dog but no cat? That's my story. All right. So if I was going to do the working for this, now in your exam you don't have to show working, but if you were going to do the working for this, you would say let D be the event they have a dog, and C be the event they have a cat. And what we want is the probability of having a dog and not having a cat. Dog and not cat. So I can literally read my sentence and translate it into math symbols. So we've got dog, and but no is the same as and not, like in English. So dog and not cat. That's what I'm thinking. That's what I want. And it should be possible to figure this out. I'm going to draw a picture of it just to make it easier on myself. So that is not 80%, but it'll do. So 80% have a cat and 90% have a dog. And so my cats are 80%. My dogs were 90%. And the bit where there are no cats or dogs, that was 5%. On the outside there. I probably should have made it not so predictable. I choose to draw a better picture. It's not going to be to scale. This bit's 80% cat, and it was 90% dog, and this bit out here was 5%, and it was neither cat nor dog. And I'm interested in having a dog, which is this bit, but not having a cat. That's this bit here. That's the bit I want. Inside the dogs, but outside the cats. That's the bit I want. Okay. What do you reckon? There are at least 5 ways to do this. It's all good. This bit must be 95% because it's 5% on the outside. So cats or dogs is 95%. And then if I took off the cats from that, it should leave me just the dogs without the cats. That's in my picture there. I'm thinking that the probability of cats or dogs is 95%. Because the probability of neither cats nor dogs is 5%. And the probability of dogs and not cats should be the probability of dogs or cats minus the probability of cats. That's the picture I've got in my head here. Yep. All right. I'll slow down and do it and be more precise about how I did it. So I'm just saying that right at the beginning they told me that 5% have neither cats nor dogs. So 5% have neither cats nor dogs, which means that all the other people must be 95%, which are the people that have at least one of a cat or a dog. That's my reasoning behind it. And I wasn't even using probability notation. Is that okay? So if I really wanted to use probability notation, I could say probability of not cat and not dog, which is the same as the probability of that. Like just from a language point of view, not cat and not dog is the opposite of cats or dogs. And that would be 1 minus the 5%. But in my head, I just did this. I didn't do the probability notation calculation. And so this is a rule we know now, that not C and not D is the same as C or D not. Neither C nor D. I'm sure in languages that aren't, some languages that aren't English, this makes more sense, but I'm also sure that it's probably bad everywhere. Yeah. And then I know that to be sure. That's the wrong thing entirely. Sorry about that. Probability of C union D is 1 minus probability of not C union D, and not C union D is the same as not C and not D, which is 1 minus 0.05, which is 0.95. That's what I was doing instead. Sorry. But I literally got it from my picture. I went, if this bit on the outside is 5%, then this bit on the inside must be 95%. That's all I did in the picture. And then from the picture, the probability of D and not C, damn it, sorry, D and not C is, well, that should be, according to the picture, the probability of D or C minus the probability of C. because it's this bit of the picture here. All of this minus that bit leaves the bit I want, which is the bit I coloured in. Which is 15%. Yay. But there are many, many ways of doing this, and some of them have better probability notation than I have. But for me, I usually just draw the picture, and since the people in your exam don't care, you could probably not worry too much about it, unless they do a thing where they go, which of these is the correct calculation? And then you would have to make sure that you can find it in your diagram. I would recommend drawing the diagram. Yeah. Yeah. Because we could have done this, we could have, no, I'm going to do an or. What if we did it this way? No, it'll never go away. There's no way of getting around this. We're going to have to use the diagram somewhere to be able to get rid of the not C on our diagram. So I am going to say in this situation, is having a cat and having a dog independent? And there are many ways to tell this, and one of them is to do conditional probability, and I want to talk about conditional probability in this context, because we don't have actual literal numbers that we can count. So we're going to have to do it a slightly different way. So the probability of C given D is going to be the probability of having a cat, but only out of the ones that have dogs. This is the formula for figuring out from existing probabilities. When I did it before, I was literally just counting objects, but if you don't know how many objects there are, you'll have to count them percentage-wise using probabilities. So this is the percentage of them that are both cats and dogs, and this is the percentage of them that have dogs. And so we know what this percentage is, we've got that, we don't have this. So oh, wait just a second. That's probability of cats plus probability of dogs minus the probability of cats union dogs. That calculation I did before works just as well if the U or the intersection is on either side. And I know what this was 0.8. And I know what this was 0.9. And I know what this was 0.95. Cool. And so that is 0.75, I think. So if we took off, that's a minus 0.05. Yeah, okay. And so the probability of cats given dogs is 0.75 out of 0.9, which is so not 0.8. Yep. No, we can't multiply the two, and I have just proven that we can't. So, but the probability of cats all by itself was 0.8. And since these two answers are different, I can't just multiply them. And so you can't know in advance that you can multiply them until you've done this calculation, and in which case you've got the answer now already. Unless they tell you in advance that it's independent, then you can multiply them. That's the final rule. So they're not independent. But if you know for other reasons that they're independent, if you know that A and B are independent from the outset, then you can do the probability of A intersection B is the probability of A times the probability of B. But only if you know they're independent to begin with. And most variables aren't. So it's extremely rare for things to actually be independent. Yeah. So I have just discovered here, this would have been the best calculation to do earlier. To get our C intersection D and take that off of the D, that would have worked as well as our calculation of C without D, D without C. So if they had said, supposing all the clients of about 80% have cats and 90% have dogs, and having a dog is independent of having a cat, then we could have multiplied them, but we couldn't otherwise. And if you don't know in advance, you can't, it just doesn't work. I wouldn't expect having a cat to be independent of having a dog. I wouldn't expect it. Because I wouldn't know which way it would go. Some people are more likely to have one pet if they've got another. People with pets are more likely to have other pets as well. But maybe it's that people with cats are less likely to have dogs because cats and dogs don't always get on, but they do quite well if you bring them up. So who knows? I have no idea what to expect. So you have to be told in advance that things are independent to be allowed to use this rule. Yeah. I mean, being a queen and being red is definitely independent in these, because I know that there's the same number, like you've got a 50-50 chance of being red whether you're a queen or not. And so that's independent. But almost everything else you can think of isn't independent. Which is why I have these, this is why I have these cards and I do the things I do, because I specifically want things to not be independent. Most card games are chosen so that things are independent. And so that's why I deliberately did not choose the card values or the colors to be my things, because they were automatically independent because cards are designed that way. Yeah. Oh, okay. So your question of when can you multiply? If you know in advance they're independent, then you can multiply to get the intersection. And lots of different situations are reasonable to be independent if they happen one after the other on different objects. So if you roll a die and then roll a whole separate die, you go, yeah, that's probably independent. Like you can just declare that it is. But anything to do with actual people or animals or something usually isn't independent. And I would not assume it was unless someone told you. Yeah. How are we feeling? Yep. Okay, we'll see how we go. Where are we up to? Cool, we've still got 45 minutes. I will answer a previous question that I've been asked, but then we'll do the estimators, okay? This is a question that was in one of the classwork things and someone has asked it, and I just wanted to talk about it because I think it's really interesting. So you've got a set of data and it has 1, 2, 3, second, 1, 2, 3, 4, 5, 6, 7, 8 with 8 numbers. And the deviations from the mean are these. What is the sample standard deviation? This one's sneaky. we need to know what the word deviations from the mean means. What does that phrase mean? What's that? It is very close to the variance. The deviation from the mean literally means how far each of the numbers in the original data are from the mean. So deviation means movement away from. Yeah, I mean, it is like the spread, but it's basically saying that if I had the actual original data and I took the mean off of every one of them, I would get these answers. That's what that means. Is that all right? Yep, okay. So let's just talk about what the standard deviation is.
Wait, sorry, one question, David.
Yeah.
Isn't always the sample standard deviation always equal to 0?
No.
Oh, okay. Okay.
The sample standard deviation is a number that you calculate from the data, and I would better write it down. So this is the formula, and it will be intimidating, and I just need to put it there for my own processing, and then I'll step away from it. So to calculate, actually I won't do the standard, I won't do it. So to calculate sample standard deviation, you have to do these steps. So step 0, before you even start calculating the sample standard deviation, is that first you calculate the mean. And then you subtract the mean from every one of the numbers in your data set. So if your numbers were like 1, 3, 7, and you, just a second, if your numbers were 2, 3, and 7, then the mean would be 4, and you would take the 4 off of all 3 of those numbers and get 3 different answers. And so you'll get a new number for every number that you originally had in the data. So I'll do an example simultaneously while I talk this out. So if I had 2 and 3 and 7, then the mean would be 12, because that's what they add up to, divided by 3, which is 4. And then I would subtract 4 from all of them. So 2 minus 4 is minus 2. And 3 minus 4 is minus 1. And 7 minus 4 is 3. That's step 1. And actually, at this stage, all of these numbers that you get should add up to 0. So minus 2 minus 1 is minus 3, then plus 3 is 0. It should all add up to 0 at this point now. And so these things that I've calculated are called the deviations from the mean. That's what these things are called. Okay, and then you take those answers that you've got and you square them all. And so now I'm going to square them. Minus 2 squared is 4, and minus 1 squared is 1, and 3 squared is 9. So just so you know, your calculator actually has a squared, most graphics calculators have a squared button, right? Like that. Gives me a 9. Be really careful. You need to include the minus 2 inside the brackets so that it does 4, because if you write this, it'll do the squared first and then the minus, but you need to do the minus before you do the squared, so you have to put brackets around it. Or know that the minus is going to go away when you square it, so just ignore the minus entirely. So in fact, that's a minus 2, just square the 2, it'll be fine. And so now we've got these 3 numbers. So you square these results, and then you add them up. And so the total is 4 plus 1 plus 9, which is 14. And then you divide by 1 less than the number of individual numbers that you had. And so the n was 3 here. And so n minus 1 is 2. And so now I'm going to divide by 2 and get the answer 7. This calculation, once you get to this point, is called the variance, the answer that you've got now. The sample variance, technically. And then the final step is to do the square root of this answer. So now I'll do the square root, and so I'll get the standard deviation is the square root of 7, which my calculator says is 2.646. That's not really edifying, it's just a number. And that process is what calculates the sample standard deviation. It's complicated.
Thank you for that.
And when they write a formula for it on the screen, they probably write that, probably. And this is the maths notation for this. X bar is the mean. Xi is the individual x that goes with it, minus x bar, that's this bit where you subtracted the mean from everything, and then you squared them, that's this bit, and then you added them up, that's what this capital sigma stands for. S makes an S sound in Greek, so it's S for sum. And then you divide by n minus 1, and then you do the square root. This is the maths version of this list of things to do. It is not important to be able to deal with this formula, but most people who have learned the maths of this cannot help but write this formula down somewhere. Just makes them feel better. Other people doesn't make them feel as much better as the mathematicians feel, but it's important to have it. It's important to know that people who have learned the maths of this like to put that down. But this is the reason we have maths notation is so we don't have to write it in words anymore. Imagine a couple of thousand years ago, before any of the symbols had been invented, not even for plus or equals, and they had to write everything in words. This is possibly going too far, but you know, somewhere in the middle is good. Okay, so that's what the standard deviation is. So my problem, so that was just an example of calculating standard deviation. For this actual problem here, they've already done the bit where they've subtracted the mean from everything. And they've gotten these answers. And so what this question that was in the course was asking us to do was to continue from this point. So now I have to square all of these numbers, and I have to add them up, and I have to divide by 7, and then I have to square root it, and that would give me the standard deviation. So they've only done one step for us, and we have to do the rest. So that's what is left to do. So I would have to do so back to the original problem. I need to square and do the sum. So 3.25 squared plus 3.75 squared plus 8.25 squared. And I'm just ignoring the minuses because it'll all turn out the same anyway. Plus 1.75 squared plus 6.75 squared plus 5.25 squared plus 0.25 squared plus 0.75 is 191.5. And then my variance will be that divided by 1 less than the sample size, which is 27.357, and then the standard deviation will be the square root of that. So I'll do the square root of the answer. Yay! I don't know how many decimal places they like, but this is enough for me. That's SD for standard deviation. So I've taught you just a little trick there, is you don't have to worry about the minuses, just ignore them entirely, and it'll come out to the same answer anyway. Yeah. So there you go. I should have checked at the beginning, actually, if these things added up to 0. Which they do, and so they really are the deviations from a mean. If you get all the deviations from the mean, they are guaranteed to add up to 0. So if they didn't, then something went wrong somewhere. Yeah. Cool. I'm just going to do one more example, just for this vibe. 10 observations have a standard deviation of 4. What is the sum of the squared deviations from the mean? Well, we do the process. We calculate the mean, we subtract it from every number to get the deviations, and then we square the results. Then we've got the squared deviations, and then we do this, add them up, which is the sum. So the sum of the squared deviations from the mean, that's this stage in the process here. And so to get from there to the standard deviation, we have to divide by n-1 and do the square root. So sum of squared deviations divide by n-1 and do the square root. That produces the standard deviation. And that answer is 4. And so to get back to here, I'm going to have to undo the square root, which is squaring, times by n-1, and that should give me this answer here. That's the idea behind it, doing this process backwards. So the variance will be 4 squared, which is 16. And then so that's the variance now. And then to get from the variance to the sum, I have to times by n-1. So sum of squared deviations is 16 times the n-1, which is whatever it is. 144, apparently. Cool. So I find that question really interesting because you know how I said that your lecturers are lovers of here's some information, how do you figure out the other information? Look at that. They want you to know the process of finding a standard deviation so well that you can do it backwards. Yeah. Cool. But at least you know that I'm capable of helping to figure these things out. So up until the exam, you can come and talk to me about it. Does that answer everything you wanted to ask? I forgot who asked me about standard deviations.
That was me. No, that's all good. Thank you for that.
Cool. Okay. And the last thing you wanted was estimations and stuff. Someone asked about two population things in regression. We spent a lot of time on probability, but I hope that was useful. Okay. Just going to pause for a second. All right. Okay, and hopefully this will get to where you want to get to, and everyone else as well. So in this course you have had, other than straight up probability, you've had several different flavors of statistics. There have been descriptive statistics where you've calculated a mean or a standard deviation and maybe drawn a scatter plot or something. And then, so those ones are like, what's in my data? But then there's inferential statistics. Does that sound like a familiar word? Yeah, inferential statistics, which are trying to abstract from the data you've got to the truth. And there are two kinds of questions that you can ask. There is a yes or no question of, is this the truth? Yes or no. And that's what hypothesis tests are for. Or there is, what is this number? And that's what confidence intervals are for. And so confidence intervals answer the question, pick some number that describes the entire population of all things it could be, and ask, what is it? So for example, what is the average times people spend on social media a day? That's a question about the population, and you would never know. But you could ask a survey of people and ask them and do an average from that and try to figure out what you think the average is for all possible people. And we know for sure that our sample is not going to be exactly representative of the entire population. And so any number we calculate as an average in our sample is not going to be the same as the population one, probably. And so we have to figure out from that a range of possible answers for the question of what is the average in the population. And when we say population in statistics, it doesn't always literally mean an actual population. The population might not even exist yet. So just as an example, what is the number of grams of fat per serving in the tubs of ice cream produced by my factory? That population doesn't even exist yet, right? Because I'm talking about the ice creams that are made by my factory in the future. And so, that I'm interested in the ones that could be made. And so just be aware that populations don't have to actually exist. They're often about the future. And in fact, almost always they really are about the future, because the only reason to do any of this statistics is to try and figure out what to do next. If you're doing it for a marketing reason, you'll go, well, what do people like? And you'll only know what people liked then when you collected the survey. And so you have to use it to try and predict the future. And so that's an interesting philosophical problem in statistics, actually. There's nothing we can do about it. And so this would be this would be an average and this would be an average, but you can also have ones where you say what percentage of school children finish all their homework every day, for example. And that number isn't an average, it's a percentage. And so you'll do different things to create a confidence interval percentage than you would for an average. Yeah, okay. Have I got in the right setup here for what the idea is? Cool. And so these ones are means, and these ones are proportions. That's what this one is here. Because statisticians, for some reason, don't like percentages unless they're saying the 5% significance level or 95% confidence level. All other percentages are decimals for them, so that's proportions. Okay, so to calculate a confidence interval for a population mean, you're going to have to collect some data and calculate a sample mean. And if you're very lucky, you won't have to use the sample standard deviation, and you can use the known population standard deviation, which is extremely rare in real life. But mostly you have to use the sample standard deviation. And depending on which of those situations you're in will change the way that you calculate the confidence interval at one key moment. But I'll do the don't know sample standard deviation, population standard deviation version first, because it's the most likely one to appear in real life. Okay, so first you have to calculate. So step 0, before you even got all of the stuff, is calculate the sample mean, which is usually called x bar, and the sample standard deviation, which is usually called S. And then we have to imagine all of the data that could have happened So confidence intervals are interesting because they match up very cleanly with hypothesis tests. So if I was going to do a hypothesis test to ask if my data seemed to suggest that the population mean really was, I don't know, 10 hours, then I could do a hypothesis test which would give me a t statistic, and I could compare that t statistic to a critical t, and then I could decide whether I rejected or retained that number. And then I could do that for every possible number and get all these different numbers that I think are consistent with the data and all these numbers that are not. That's something that one could do. But instead of doing that, we're going to reverse the calculation for the test statistic and turn it into a calculation for the confidence interval. So the next stage is to figure out a critical value of the t statistic. Does the phrase critical value sound familiar? And the way you do that is you pick the one that has, if it's a 95% confidence interval, you pick the one that's got 95% in the middle of your t distribution. Like that. But if it was a 90% confidence interval, you'd pick the one that had 90% in the middle. And if it was an 80% confidence interval, you'd pick the one that had 80% in the middle. And so somehow you have to get that from like a t table or a computer or something. I think they will provide one. they have always provided one in the past, but again, every semester's new. They've always provided a T table and a Z table in the exam for this course. But again, it's like it just reminds me of a superannuation ad. Past performance is not indicative of future performance. They've always provided one. You can't fit that on your sheet. And this will be different depending on the sample size. And so you'll have to do the degrees of freedom will be the sample size minus 1. And go look up the correct T statistic for your T distribution in the T table that goes with the 95% confidence interval, or the 90%, or the whatever percentage it is. Yeah. So in general, it will usually be around the number 2 somewhere. If you were using a Z, it would be exactly 2. It would be exactly 1.96. If we're using a T, it'll usually be a bit bigger than that. So it'll be bigger than 1.96 usually. And if you're really unlucky, it'll be over 2. And so that, in my book, they always call that thing T star. I don't know if what your lecturer calls it. No? They call it T crit, T alpha on 2, something like that. So the alpha they're referring to is the other percentage. So it's 95% in the middle. The alpha is the 5% on the outside. If it was a 90% confidence interval, the alpha would be 10%. And the reason it's alpha on 2 is that 5% is spread evenly over this top end and this bottom end. And so only half of it is on this side. And when you look up a T table, it normally tells you what one side of this is and not both sides. So that's why the alpha on 2 that they're referring to. Okay, and then your confidence interval has 2 ends. It has a top end and a bottom end. So the right-hand end of the confidence interval is the sample mean plus the T alpha on 2 times the S on root n. And the left-hand end of the confidence interval is X bar minus this thing. You're welcome. And I don't know if they do this in this course, but this part of the calculation is called the margin of error. If you ever hear that phrase, that's what it means. It may or may not be in your course, but that's this bit of the calculation here. That's what it's called. And this bit here, that bit there is called the standard error. That thing there. That's a bad word, just a second. That thing there is called the standard error.
Hey David, one question I've got with that, sorry.
Yep.
So with the T O over Z, is that just your score from the T table?
Yes, it is. It's an alpha divided by 2, actually. I normally just call it T star, but I'm basing it on what people are telling me that they see. Yes, that is the score from the T table.
Perfect, thank you.
And that's the confidence interval. And normally when you report it, you just tell them both numbers. And so just as an example, suppose you collected data from like 16 people and the sample mean social media hours was 8 hours per day with a standard deviation of 2 hours per day. Find a confident 95% confidence interval for the true mean number of social media hours. And so you've got the sample mean, you've got the sample standard deviation, and so we need the critical t. And so that's we've got the degrees of freedom is 16 minus 1, which is 15, and we'll have to go look up in row 15 of the t table what the best one is. And your t tables will all look different depending on what course you're in. And I don't have access to my uni, so I've only got Google. So this is the first result that Google gives me, this one here. It's probably fairly similar to yours, and it's quite interesting that it'll give you cumulative probabilities and stuff like this. And it also, down the bottom, this one gives me confidence levels. So if I go to the 95% confidence level and I scroll up to row 15, I get 2.131. And so that's great. But if yours doesn't have a confidence level bit, you'll have to go to the two-tailed probability of 0.05, because that's the other probability, 95% in the middle, 5% on the outside, and go down to row 15 and it's 2.131. And as you can see, the bigger the degrees of freedom gets, the closer it gets to 1.96. And the infinity row, some tables call this row infinity, but it's the row for Z instead of T. Z or T tables with a calculator. Cool. Are you allowed a graphics calculator in your exam? Cool. So an ordinary calculator, just a second. While we're at it, so this kind of calculator here will not do Z and T calculations. You have to have either the brand new Casio 82000 AU Plus, which is a brand new calculator just released like in the last month in Australia, which it's a scientific calculator, but it has a couple of extra bits and it's got the T and Z tables in it. Which is very nice. So it's got to be cheaper than a graphics calculator, or a graphics calculator, or a Casio, or a TI, or whatever it is. And you would need a calculator that has that in it, and I don't have one handy.
So do you think that we'll be expected to have one for the exam, or?
I don't think you're expected to have one for the exam. My instinct is that because your lecturer has said she doesn't mind whether you calculate it with a calculator or with Excel or with tables, she's going to provide tables.
Oh, okay, that's good.
So that if you don't have a calculator, you can still use the table anyway.
All right, that's what I was worried about.
That's my instinct. And it would be bad of her if she didn't. But this would be a very important question to ask in the discussion board, to say, will there be T-Z tables provided in the exam? That would be great to know.
Yeah, I might have a bit of exam anxiety after my physics exam, where they just randomly started taking away our formula sheets because they forgot to print enough for the other group.
Oh man.
They were like, hey guys, do you reckon you could share a formula sheet, one between two people? We were like, I mean, we could.
So they will not do that in your big exam in Wavell Hall. It is too complicated for them to do something like that.
No, thank you. That's good to know.
Yes. T. Yep. You do a Z. Yep. I will repeat that properly on paper in a second. I'll finish this calculation. And so the right-hand end, you could call it the right-hand end because it's talking about left and right for bigger and smaller, or you could call it the top end and the bottom end. It doesn't really matter how you do it, or the high end and the low end. the right-hand end of the 95% confidence interval is the x bar plus the t times the s on root n. So in our case, that is 8 plus 2.131 times 2 on the square root of 8. No, how many? 16 people, sorry. So really important that this isn't n minus 1, it's just n. The n minus 1 is for figuring out what the correct t is. And then that on my calculator would be 8 plus 2.131 times 2 divided by the square root of 16. And this calculator is clever enough to know to do the square rooting and the dividing before it does the plus, so I don't have to put any brackets in, and it will produce 9.06. I'm just going to use all decimal places, just leave it at that. Whereas the left-hand end of the 95% confidence interval will be the same, but with a minus. And if you've got a nice scientific calculator, you can go back and delete the plus and put a minus instead. You get a 6.9345. And then your final answer would be the 95% confidence interval is 6.9345, 9.065, something like that. 4 decimal places seems a bit overkill, but whatever. Is this familiar, this brackets comma thing? Yeah. You're also allowed to say it with the words from 6.9345 to 9.0655. But if your lecturer has used this notation, then use it, it's shorter. Yeah. Again, in a multiple choice test, you'll just compare with what you expect it to be. Yeah, but just to say that if you don't know, so if you have, or if you know the population standard deviation, then it's calculate x bar and just know the standard deviation sigma. And it's written as a sigma now instead of an S. That's the main difference in terms of the notation. And you'll find the critical, and this time it will be Z. So there will be no degrees of freedom because Z doesn't have degrees of freedom, it's just Z. And so you'll do the exact same thing. You'll find the Z that's got 95% in the middle, or 5% on the outside, or whatever percentage it is. And then your confidence interval right-hand end is x bar plus Z times sigma on root n. And the left-hand end would be x bar minus Z times sigma on root n. So there's still a dividing by root n, that's still there. That's really important. The idea is that the confidence interval should get narrower the bigger n is. Because the more information you've got, therefore. Yeah. And so you could totally imagine an exam question that says, you do it with n equals 100 and do it with n equals 1,000 and see what you get. And the one with the bigger n will get narrower. And so because you're more sure about what the population mean really is. And so the way to interpret this is you would say this one here, you say we are 95% confident that the true mean number of social media hours per day is between 6.9345 and 9.0655 hours. 95% confident that the true mean social media hours is between 6.9 and 9.1 hours, something like that. That's how to interpret a confidence interval. You're not allowed to say any words with the word probability in them when you interpret a confidence interval, because it just ends up being wrong from a probability point of view. The probability is referring to if we imagine all possible data sets and imagined all possible confidence intervals that we could have calculated, 95% of them, there is a 95% probability of collecting data that produces a confidence interval that does contain the mean. That's where the probability is. But that's too hard to say, so we just say we're 95% confident. Yeah. Cool. And there is other formulas for doing confidence intervals for proportions as far as I'm aware. Have we done that in this course? Maybe not? Okay, I won't mention it then. When you're doing your study it turns up, then we can talk about it. So if you want to do a confidence interval for proportion, that'll be a whole other thing. It'll be similar, it'll be something plus a bit, something minus a bit, but the bit will be calculated differently because it's not a mean, it's a proportion. Cool. Any other questions about this? Sweet. I'm going to have to stop there. It's been a long day and it's time to stop. Thanks for having me. I'm going to turn off the recording now.